El invitado de hoy es el profesor Ross Stein y Allen es quien va a hacer la semblanza, ya que él conoce muy bien todo el currículum y la trayectoria del Dr. Stein. Thank you very much for being here today.
Gracias. Tenemos con nosotros hoy Ross Stein. Él actualmente es el CEO de Temblor.net y creo que al final va a mencionar algo con respecto. Él estudia la interacción de terremotos tras la transferencia de estrés, pero no estoy leyendo en inglés, entonces estoy haciendo introducción. Él es el presidente actual de la sección de Tectonophysics de la AGU. En 2012 recibió el premio de la AGU de peligros naturales. Además ha hecho la conferencia de Francis Birch, la conferencia de Gilbert White. Son varias conferencias que están durante la AGU cada año. Y las fronteras de geofísica también. En 2012 dio una de estas prácticas que se llaman TED Talks, que se llama Defeating Earthquakes, o sea, enfrentando los terremotos. Además dio la conferencia magistral de... perdón, toda la traducción. Bueno, lo voy a decir en inglés, ni modo. The Presidential Awards for Excellence in Mathematics and Science Teaching. O sea, de enseñar en ciencias y matemáticas por excelencia un premio de presencial. En 2012, en el invierno de 2012, dio la conferencia distinguida en Stanford, en el Colegio de Ciencias de la Tierra. Y bueno, voy a brincar ahí mucho, perdón. Recibió su licenciatura de la Universidad de Brown con honores y recibió su doctorado de Stanford. Él es miembro de la AGU y está aquí porque hay una serie de prácticas del Geological Society of America. Y entonces él es parte de esta serie de prácticas, entonces ellos en parte están pagando su boleto de avión para venir aquí. Además, en 2003, en los 10 años previos a 2003, fue, según el Science Citation Index, segundo, el científico de terremotos segundo más citado. El número 1 fue Kanimori. Y de 1900 a 2010, él fue el 10º más citado. Y ha recibido mucho más premios y ya estoy, creo que ustedes han escuchado suficiente para saber que muy interesante lo que él hace y además que da buenas prácticas, entonces ya tenemos el gusto de escucharlo hoy. Thanks, Ross.
Thank you, Alan. Over the last 6 months, I've had a lot of contact with Alan and Gerardo and Sholi as I've tried to understand the earthquakes that have befallen your country. And the purpose of this conversation that I would like to have with you today is to share with you our preliminary thinking and understanding of what these earthquake sequence might mean, and to solicit your views and your reactions to what we're thinking about. So in this map, we're looking at a 1-month period of magnitude 3 and larger earthquakes in a region about the size of California. During that same month, California had 30 magnitude 3 and larger earthquakes. There are 3,300 in this picture. So this is certainly a remarkable period. Now, here's the argument I'm going to make. That is that some of the earthquake interactions that we are seeing here are promoted by the permanent transfer of. There is a possible role of dynamic stress transfer. Not sure if I'm doing anything here. There's a possible role of dynamic stress transfer between the Tehuantepec earthquake and the Puebla earthquake. I'll show you the results on that. It's equivocal. It's something to discuss and not really be certain. We also are making a one-year forecast for magnitude 7 and larger earthquakes in this portion of Mexico. And we think that there is a high likelihood of having such an earthquake in the next year. So it may not be over. Okay, let's begin by just looking at the observations, the increase in seismicity rate during the last several months compared to the preceding 15 years, using the Yunnan catalog. So if it's red here, there's 100 times increase in the rate of earthquakes. If it's yellow, it's a 10 times increase. And in the one little place that's blue, it's a drop by about a factor of 10. That little blue drop is probably in the noise. So the big picture here is the very wide range of aftershocks associated with these big earthquakes, particularly extending up to the north of the Tehuantepec rupture. And although, because seismicity is very rare in the region around Puebla, we don't have as good a record, it looks like Puebla also has a broad region of about 80 kilometers in which seismicity rates have increased. Now on the left are shallow earthquakes, 30 kilometers and less. On the right are deeper earthquakes. So the pattern is different, reflecting the subduction process and the second bend occurring here. Okay, on what faults are these earthquakes occurring? And the best way to try to image that is to look at the CMT focal mechanisms, and here we're using the global CMT catalog. And in blue are all the earthquakes that occurred before September 7th, and in red, the ones that have occurred afterwards. So the red are the biggest aftershocks, if you like, in the sequence. So at the shallow depth, it's characterized largely by megathrust earthquakes, except for outer rise normal faults out here, and not much else. At a greater depth, we have some thrust earthquakes, but we also have a great deal of normal faulting events in the slab, principally in the slab. And we have the kind of rough zone of the aftershock of each of the three large earthquakes, the two 7.2s and the 8.2. Perhaps the simplest target to analyze is the relationship between the magnitude 8.2 and its 6.1 aftershock. And that's shown here. So this is a Coulomb stress calculation. In red are the areas where the shear stress has increased and the fault has been unclamped. It's the combination of those two factors. Essentially, it's where the shear stress has increased plus half of the unclamping. So red area, the faults are believed to be brought closer to failure, and in the blue area, we call them stress shadows, or where we think faults have been inhibited from failing, and you can see that this earthquake lies in a red zone. The same kind of analysis can be found for the relationship between the Pinotepa Nacional earthquake and the magnitude 7.5 earthquake that occurred in 2012. Pinotepa is right on the periphery of the rupture zone of the 2012 earthquake, and it was brought very close to failure by that event. You can think of the Pinotepa 7.2 earthquake as a late aftershock of the 7.5 that occurred in 2012. Now, when we look at the stress distribution caused by the big earthquake, it turns out to be highly depth dependent. So here are two images, one at 30 kilometers depth and one at 70, and they look quite different in terms of where we would expect faults to shut down. Those are the blue stress shadows, and where we would expect them to turn on and produce aftershocks. Those are the red zones. And you can see why in a cross-section. The Coulomb stresses combine areas where the shear is increased, principally here, and where we've unclamped faults, here and here. And so we have this depth dependence to the aftershocks. Now in this calculation, we're assuming that all faults are parallel to the main rupture and have the same rake, the same sense of slip. It's one assumption of many one could make, but any geologist will tell you all faults don't have the same orientation, so it's only an approximation. Another way of doing this is to use the nodal planes of background earthquakes, earthquakes that have occurred over the last 40 years, as proxies for nearby faults. So let's show you that one. So here we're using global CMT focal mechanisms during the 42 years before this main shock. And we're calculating the Coulomb stress on both nodal planes of those focal mechanisms. Now, if friction were zero, the shear stress on those two nodal planes, since they're perpendicular, is the same. But if friction is not zero, and it's probably something closer to 0.4, then they're different. So we have an ambiguity. This is the yin-yang of seismology. We don't know which of those two nodal planes is the fault plane. So here what we do is we calculate it on both planes, and we use the plane that has the most positive stress change. So this blue area here means that regardless of which plane you choose, these faults should be shut down as a result of that big nearby earthquake and should not produce subsequent shocks. And not only do we see it that way, we see it in the way I showed you before, this big shadow, and we see it in the seismicity rates from the UNAM catalog. So you can see that the seismicity rate decreased after the earthquake in this boxed area. So that's evidence of the impact of the stress shadow. So even though earthquakes tend to produce other earthquakes, there are regions close to a shock where the stress transfer tends to shut them down. This is one. Another more obvious example is after the great 1906 earthquake in San Francisco, the rate of magnitude 6 and larger earthquakes in the San Francisco Bay Area dropped by an order of magnitude in the 75 years after 1906 compared to the 75 years before, because all those faults were in the stress shadow of the 1906 earthquake. So stress shadows matter because they are the places where we reduce the hazard and the likelihood of future earthquakes. Now, I referred previously to the relationship between the 2012 magnitude 7.5 earthquake in Pino Tepa. You can see that it's on the periphery of the other rupture zone. We also noticed in the 5.5 months after the Tehuantepec earthquake, but before Pino Tepa Nacional, there is an increased rate of seismicity in the future site. So is that something that was caused by Tehuantepec or not? And when we look at a time series of the UNAM catalog, we see that it is not strictly at all related to the occurrence of the September 7th earthquake, which is here. It just seems to have started to increase its rate somewhere around 2015 for reasons that we don't understand. So that increase that I showed you is nothing, I think, that could be considered precursory. Why the rate changed, I don't know. This is more typical. We have the earthquake, the aftershocks decay, but then it started to depart from the long-term rate. Well, what about Puebla? Puebla is an earthquake of magnitude 7.2. Of course, we all recognize it had very few deep aftershocks, but it did have quite a few shallow aftershocks. So this is a bit complicated, but the color, or the shading of the earthquakes indicate their depth. So all these dots here are very shallow earthquakes. These gray earthquakes are deeper. The colors here indicate rate change. So this is a rate change after Puebla compared to before. So everything that's red actually has a higher rate of seismicity after Puebla. So these red regions are really Puebla's aftershock zone. Now, can we explain that in terms of Coulomb stress transfer? The answer is kind of. Here's a calculation of the Coulomb stress transfer at the depth that these aftershocks are occurring, roughly about 5 kilometers. And if we cut out the areas in gray where we don't have any data, because we don't have any preceding earthquakes to compare the rate change, you can see that there's some potential relationship of the Mexico City area turning yellow or red, and some of the area down here. So it's possible that the rate increases that are found, that you probably felt here in Mexico City, are actually related to Puebla, even though they're very, very shallow compared to the earthquake. Now, what can we do with these insights? What we're seeing is that the magnitude 6 aftershocks of Tehuantepec and Pinotepa Nacional and the vast majority of the smaller earthquakes are occurring in places that were brought closer to Coulomb failure. So we would like to use that to make a forecast for the next year for large earthquakes. And we do that using the theory of rate and state friction developed by Jim Dietrich. And I'll show you how it works. So imagine we've had an earthquake here, a strike-slip earthquake, and we're out on the fault and out beyond the end where we've had a sudden 1 bar stress increase. And by the way, earthquakes, as you know, drop stress by somewhere around 30 bars. You can put a bar of Coulomb stress across your palms if you just put very little contact area and push as hard as you can. So a bar is not a lot of stress, but a bar turns out to be plenty of stress to turn aftershocks off or on, which is interesting. And you can think, not only is that a small amount of stress with respect to the stress drop, if you think of the total stress that those faults are under, probably about 1,000 bars. The fact that 1/10 of a bar of stress increase could be important is amazing. So here we have this 1 bar stress increase, and this is what we expect in terms of the seismicity response to that stress increase. Because it's sudden, there's a jump and then an Amori-like decay. And so what this tells us is, in the rate state Coulomb world, what the stresses do is if you have a stress increase, it simply amplifies the background seismicity rate. If there were no earthquakes in the area, the stress increases have no effect. Stress decreases suppress the background rate. Again, if you had no earthquakes, no effect, but if you have a lot, you will see a decrease. So that's how the theory of rate state friction works. And so for this, what we need to know is the aftershock duration, how long it takes the aftershocks to decay to the rate that we had before the main shock. And we need to know something about the stressing rate of the faults. And we also need to use the catalog. Now we're using the UNAM catalog for this purpose. And at levels of magnitude 5 or 6, the UNAM catalog agrees extremely closely with the global CMT catalog and the independent ISC GEM catalog. Their subtle differences can be explained by how they are operated. But there are differences below magnitude 5. The B value above magnitude 5 is 1, and below magnitude 5 is 1.5. So I suspect that there is some grade inflation. There's some magnitude inflation going on, possibly because of a change in how magnitudes are calculated at the smaller level. And so what's called a 4 in the UNAM catalog may be actually closer to a 3. That's something that we could discuss. And then we need to calculate or project the aftershock duration. And we use Tehuantepec for that. So the x-axis is time here. And what we want to do is project when the aftershock decay will go back to the rate that existed beforehand. These are various ways you could do that. And we end up with a number of about 5 years for the aftershock duration. And just as an aside, the higher the stressing rate, the shorter the aftershock duration in rate and state friction. So if you're on a megathrust zone, it's all over very fast. But if you're in some place that has a very low stressing rate, let's say New Madrid, Missouri, that had big earthquakes in 1811, 1812, the seismicity we see there today could very well be aftershocks, because its aftershock duration is probably 200 years long, not 5 years long. Okay, so these are the constituents. So now what we need to know is the background rate of earthquakes, and that's shown here for the shallow depth, below, above 30 kilometers on top, and below 30 kilometers below. So this is just the 15-year rate of background earthquakes. And if these 3 events had not happened, we would predict about 43% chance of getting a magnitude 7 in the next 12 months, just from long-term background processes. I was in the SSN room with Sholi this morning, and on the glass are all the lists of magnitude 7 and larger earthquakes since the turn of the century. So you can see, yes, 7s have a very high rate of occurrence here, even if we didn't have these events. But now we add the Coulomb stress effects of these 3 earthquakes to this picture, and that's what's shown on the right. And you can see the differences at Pinotep are very subtle because it's relatively small. The differences you can't even see because it's too washed out a yellow, of Puebla, but the effects of the big 8.2 are very broad. You can see how different this pattern looks and how different this pattern looks. So the principal reason why we calculate an increased rate of magnitude 7s is because of that large earthquake. And so if you like, a 7 could easily be a delayed aftershock of that magnitude 7. And so what we're getting now is an increased rate of large shocks by about a factor of 50%. And we're forecasting basically 1 magnitude 7 in the year. 1 magnitude 7 corresponds to 63% likelihood of occurrence. So the problem with a forecast like this is it's not principally testable, right? Because if the earthquake occurred, I can say, oh, we were right. And if it didn't occur, I'll say that there was a 36% chance that that would occur, and I'll be in great shape. Yes?
So is your forecast for the red area in your bottom right figure?
Yes, the forecast is for the entire area, but almost all the earthquake occurrence will be in the red areas. So if we had an earthquake in a white area, it would be very inappropriate of me to say we were right. That earthquake not only needs to be on the map, it should be in a red or at least a yellow area. So your question is a very good one. Okay, but that leaves the question that's been gnawing on all of our minds about whether Tehuantepec is related to Puebla. And one possibility that we always need to consider is that they're coincidental. And that's important given the high rate of magnitude 7s in this area. So are they? So I want to show you 2 ways we've tried to calculate this. The first is, well, what's the chance that we'd have a magnitude 8 or larger, followed by a magnitude 7 or larger, let's say within 2 weeks at distances of somewhere greater than 300 kilometers and less than 700. We took the global CMT catalog and we reshuffled the times of earthquakes. And then we did 10,000 shuffles of the entire catalog. And we found basically 120 cases where that occurred in 420,000 simulated years. Okay, that's 1 chance in 3,500. All right, that's one way we can answer the question. That's not necessarily germane to Mexico. We're using the entire catalog because we're trying to see how often does this occur anywhere on Earth. All right, what's another way to do it? We'd use the birthday paradox equation. Okay, my birthday is September 28th. Does anybody in this room have my birthday? Aha! Okay, that is fantastic. I didn't ask you to come, but I'm so glad you're here. We have a conversation we can have afterwards. Okay, so the birthday paradox equation is very interesting. It's exactly this. Now, in the birthday paradox equation, we don't care about the fact that my birthday was on September 28th. We only care that somebody has my birthday. So in that case, I don't care that it's a magnitude 8. I only care that the magnitude 7 is in the room. Okay, so let's look at the birthday paradox question. So what we need to know is what's the independent likelihood of the Puebla earthquake, of a 7.2 at that location. And for that we use the global earthquake activity rate, or GEAR model, which says that the likelihood at that location within a 100-kilometer diameter area is 0.05% per year. Okay, and then we use the birthday paradox equation, which is a horrible factorial, to convert this to a span of 2 weeks, and we get 1 chance in 500. And you say, wait a minute, which do you believe? 1 chance in 500 or 1 in 3,500? Well, we've asked different questions. Dave Jackson advocated for the birthday paradox equation because he said you never would have asked the question unless that magnitude 8 occurred. So you shouldn't put that in. You care about the 7. I only care about her birthday. But you can do a sanity check. Say, all right, let's say you wanted to consider the likelihood of the magnitude 8. That has about a 1% chance per year of occurring, because it's a more active part of the megathrust. If you put that in and you multiply this number times 100, 1 in 100, then these two estimates are similar. Okay, so now you can say, well, 1 in 3,500, maybe 1 in 500. Is this extremely rare or not? And the best sanity check we have is this coincidence. I think we would all agree that the earthquake would occurred within 2 hours of the annual drill. That's a very easy calculation to make. It's 2 hours divided by 365 days, and that's almost one chance in a million. And that is a coincidence we all lived through, you more than me. So that makes these numbers look very small, and that makes a coincidence look pretty possible. But when I started out as a young scientist, my mother, who's a calligrapher, sent me a piece of calligraphy that she made for me. The great words of Alfred North Whitehead: "Seek simplicity and distrust it." So the story I've given you is simple, it holds together, but we shouldn't trust it. We should turn over the stone and say, could they be related? And if so, how? So I went over to Fred Pollitz's office at the USGS, a colleague of mine, and begged him to run some very sophisticated calculations of the dynamic stressing from Tehuantepec to Puebla to see if we could, let's just look. What's the situation there? Now, let me tell you a little about this. In dynamic stressing, you can't use an elastic half space as we do in the static calculations because waves are bouncing off all the different layers. So Fred uses a spherical harmonic calculation with many, many layers. And we need to use the actual source for the Tehuantepec earthquake, how the rupture grows in time, because each one of those little segments pops off waveforms. Basically, the waveforms are being shed as the rupture accelerates and decelerates over about, 60 seconds, 80 seconds that it occurred. And then they bounce off all these layers and they head in the direction of rupture propagation to the northwest. So let me show you what Fred came up with. So first, you should also know that he's using a 20-second corner period. In other words, anything you're seeing here had a duration of at least 20 seconds. Okay, one other aspect of this is that we need to know not only the source, we need to know which of the two nodal planes of the Puebla earthquake is the real one. It matters. So on these figures, I'm going to show you a set of 3 slides. Nodal plane 1, and it's arbitrary what's 1 and what's 2 is on the left, and nodal plane 2 is on the right. So this is the transient shear stress, and you can see that it's pretty high, about 3.5 or so bars for nodal plane 1, little lower for nodal plane 2. Okay, so what that is, that's not the shear stress in this. That's the shear stress in the direction that we think the Puebla earthquake ruptured. All right, what about the normal stress? The normal stress, terrible word normal, it's the unclamping stress. Okay, so here's the normal stress. And this is the zinger on the left. That's 6.5 bars of unclamping over 20 seconds that seems to have occurred if the rupture was on nodal plane 1. If it's on nodal plane 2, it's much smaller. It's a little over 3 bars. All right, what about the Coulomb stress? I've been arguing in the rest of this talk, it's the Coulomb stress that is really responsible for producing earthquakes because you both increase the shear and unclamp the fault so it can go. The Coulomb stress is pretty low. It's on the order of 2.5 or so bars in both cases. Now you might say, well, wait a minute, why is the Coulomb stress so low? If you had 6.5 bars of normal stress and we divide that by 2 because of the friction coefficient and we add that to the 3.5 bars of shear stress, why aren't we seeing a much bigger number here, something like 6? And that's because the peak shear stress doesn't coincide in time with the peak unclamping stress. Now we have to worry about that. Okay, so the Coulomb stress doesn't look that large. So it all boils down to this. This is the thing, it's almost a bullseye, and if the strike, what we're suggesting here, it could be a bullseye. And there are lots, we know from the CMT focal mechanism, there are lots of faults that have the same orientation broadly in the Mexican highlands. So is it possible that it picked out the fault that happened to be in harm's way? Now, Shirley this morning said to me, Amos Noor says everything can be explained by fluids. Well, there's a possibility here. Imagine that you strongly unclamp the fault over 20 seconds. Maybe that would give some tiny room for fluids being produced by the sediments that are in the slab that is now downward bending to get those into the fault zone. And then you needed some amount of time for those fluids to diffuse in the fault zone and make it slippery. Now that is pure speculation. I've got no evidence that this occurred. And when you think about it, you know, I mentioned before 1,000 bars of lithostatic load. Well, if you unclamp by 6 bars, you're not opening this fault. You know, nothing near. But if the faults are at near lithostatic pressure, and if fluids are being driven off the slab as it starts to bend and go down, maybe it's a process. Now, 2 problems. One, it's not clear that the rupture occurred on nodal plane 1. Gavin Hayes' finite fault model produced by the USGS, he chose nodal plane 1. Diego Melgar and others chose nodal plane 2. And if it's nodal plane 2, the effect is much smaller. Okay, here's another problem. It sure looks like the slab is torn. If it is torn or severely warped between Tehuantepec and Puebla, then that might strongly diminish the transmission of stress or disrupt the transmission of stress. That's not included in our model. It's a spherical layered model. So, you know, this is something that would need to be accounted for if you wanted to fully understand the problem. So where do we go from here? It seems to me that where do we go is, well, is there any seismic, geodetic, or evidence that you in the room have that might bear on this question? This is really why I'm here. Is there anything that we can come up with to falsify this hypothesis or to find some kind of corroborating evidence? I don't have an answer. I'm guessing that the answer might be in this room. But the one thing I can do is say, all right, is there anything else like this that would give us more confidence that this was possible? And I want to show you 3 cases that each of them bears some resemblance to this, but they don't look just like it. And the first is the 2012 magnitude 8.6 Indian Ocean earthquake, which is the largest strike-slip earthquake ever to be recorded by a factor of 10 in seismic moment. And this earthquake launched global aftershocks all around the world up to magnitude 7. Just compare the earthquakes around the world in the week before versus the week after. Those colors are the love wave radiation patterns. And we found the best way to fit this was not to look for the highest stress, but the longest duration above a critical stress. Duration really seems to matter in this business. If it were just the magnitude of the stresses would be read only near the star. But the earthquakes are uniformly distributed around the globe. Now, this may or may not look convincing to you because actually these earthquakes are occurring where earthquakes normally occur, around the Pacific Rim, etc. What really clinched it, and when I should say something here. I didn't believe that this was possible. And I kept getting buzzed on my phone that there were earthquakes occurring. And I went into my office about a day later and I made a plot like this, just the earthquakes, no colors. And I convinced myself it wasn't significantly different. And Fred Politz came into my office and he said, Ross, have you seen all these earthquakes? I said, yeah, but they're not aftershocks. He said, yes, they are. And we went into his office, and basically he showed me this. And I was sitting on the same data, public data that he was, but because of my biases, I refused to see it. And this is one of those great moments in science that when you discover that your wisdom and judgment can actually be bias, and you need good colleagues to slap you and tell you that you're blind to what's in front of your eyes. And I think this happens over and over in science, and we all have to be on alert for it. So this is obvious that this was this global phenomenon. We said, okay, if this can happen for an 8.6, then what about the 9.2 in Sumatra? What about the 9 in Tohoku, etc.? We've had 5 earthquakes this size or larger in the last 10 years. Do they show it? And the answer is basically they don't. If they show it, it's just peaking above the noise, and that's when we stack them. So we said, why is this earthquake different? And the biggest reason is that it's a strike-slip earthquake. And strike-slip earthquakes are much more efficient at producing love waves. Okay, what do love waves do? A lot of people here think they know what love waves are, but that's not that kind. Love waves do this. They go back and forth like this. So if you were a strike-slip fault, love wave, a vertical strike-slip fault, love waves would probably have a big impact on you. So we said, okay, let's look at strike-slip earthquakes around the world. And we saw this. Normally, only a quarter of the worldwide earthquakes are strike-slip. Like half of them are thrust and some are normal. But during this period, the rate of strike-slip earthquakes rocketed up to 70% and then decayed like a very fast Amori law. Now let's think about that with respect to the Puebla delay, this very long delay. So on the one hand, everything seemed to be over in a few days for this big earthquake, but you can see that something's still going on 12 days later. So maybe Puebla's still in the range when we're thinking about the time delay. So it's not the same deal. An 8.6 is not the same thing as an 8.2. It's, what, 30 times larger in size? But it suggests that under some circumstances, things like this are possible. Okay, let me show you another. This is recent. This happened in the last year, a magnitude 6.7 earthquake on the Greek-Turkish border, and the Bodrum Kos earthquake. And what I'm showing you in red are the earthquakes that occurred during the first 16 hours after that event. And they sure seem like they sent out a jet of earthquakes to the north, 400 kilometers to the north. And this is a small main shock. It's a normal shock, like Tehuantepec. It's much smaller, but it's reached out almost the same distance. These are very small shocks, so it's not triggering a magnitude 7, but you can see that there's some resemblance here. And we thought we could explain this by looking again at strain. What we now need to do is redo the analysis for this earthquake that we did for Tehuantepec, looking at the transient unclamping and shear stress. Okay, here's the last one. This is the magnitude 7.8 Gorkha, Nepal earthquake, a thrust event. Now it's starting to be almost as large as Tehuantepec. And it produced 3 remote aftershocks, less than 5.7, that might be related to the dynamic stress, could be related to the static stress. One of these is way over here. This is a 5.3, 15 minutes later. And that one is really interesting. So here it is, and I want to show you the seismograms. So we're sitting here at a station in Japan, relatively close to this earthquake. The P wave comes in, PPS, and then this magnitude 5 starts, and it strengthens when the double S comes through. So this is a smoking gun, right? This is the kind of dynamic triggering we'd really like to see, because when the waves hit, the earthquake occurs. For whatever reason, that's all too rare. None of the 5.5 and larger earthquakes after the 2012 event occurred when the waves arrived. They're all delayed. So the reason for the delays isn't clear. So I think what this kind of set of comparisons does. It just says it's possible. Nothing looks quite like this, but there are some resemblances to things that we've seen. All right, where does this leave us? This is tantalizing. It's possible. It's not clear. We need corroborating evidence because a calculation is just a calculation. It's not reality. Independent of that, I think our forecast for an increased rate of earthquakes is sound. We will see what happens. And I want to, since I brought my mother in earlier in the talk, I want to leave with a piece of graffiti I photographed during the AGU meetings on a warehouse wall in New Orleans. If you can't read this, it says, "Tell my mother I love her." And someone else has written, "Tell my mom I see how it is." So here's to moms and good colleagues. Thank you.